Another application of double integrals has to do with mass and something called the center of mass. Now we're going to start by considering what are called point masses. So these are just objects with mass but negligible size. We're going to place these point masses on a line, so something like this configuration. These masses on the line are now going to be placed on some sort of pivot or fulcrum. Where should we put this pivot so that this line balances horizontally against gravity? So in order to answer that question, we have to introduce coordinates on this line. And that means we'll have an x-axis, something like this, and somewhere along this x-axis will be an origin. The distance from this mass to the pivot here is called d1, whereas the distance from the pivot to the mass here is called d2. Our goal is that we want to balance the moments of each mass. Now, what is a moment? So a moment is another way of saying the moment of force, the mass times the distance away from the pivot. We would like to balance this m1d1 with m2d2 for this mass configuration to balance against gravity. We're going to say that mass 1 lives at some location x1 and mass 2 lives at some location x2 on that line. The location of the pivot is at some x bar. d1 is x bar minus x1, so we'll take larger x minus smaller x to calculate that first distance. And we want this to be equal to m2 x2 minus x bar. So what we're going to do is solve this equation for x bar. m1 x bar minus m1 x1 is m2 x2 minus m2 x bar. So we're going to group together all the terms with the x bar, m1 plus m2. So at the end of the day, what we find is an equation for the location of where that position x bar should be. Now, upstairs, this is what we're going to call the total moment, because it's the sum of both of these moments, and we'll denote that with a capital M. And down here is the total mass of the system, and we'll denote that with a little m. The center of mass should be placed according to this calculation. And when we do that, we can have differing masses live at differing locations from the pivot. There will be a horizontal balance. Now we can extend this to many point masses, m1, m2, all the way down to mn. So if we have all of these point masses on a line, m1 that lives at location x1, m2 that lives at location x2, m3, location x3, so on and so forth. We end up going through exactly the same calculation, and what you will find is that all of the moments added up upstairs in this expression divided by all of the masses being summed up. Another more compact way to write this is that it would be the sum from I equals 1 to n of all of these individual moments divided by the sum I equals 1 to n of all of the individual masses. Once again, total moment over total mass. Now, we're not going to stop there. This is an important next step. Where we want to go is into continuous distributions of mass. Now, what we considered above were what are called discrete masses, which means they're all concentrated in some point locations, but a continuous mass distribution has a little bit of mass spread out over all points along a line. So we're going to consider a 1D continuous mass distribution. We've got some sort of line, but it has varying mass. Now, it could be the case that for here we might have lighter mass, and it could be over here that we have heavier mass. Now, the proper way to describe this mathematically is to talk about a mass density. Now, in this particular case, it's going to be a linear mass density. It's going to measure mass per length at any given point. We are going to attach a coordinate axis once again to this line distribution, and the density function will be a function of position along this line. Subdivide this mass distribution into n equally sized subintervals. Now, if the bar here starts at A and ends at B, we're going to say that each one of these subintervals has a width of delta x And what we're also going to do is create a partition. We'll say that x0 is the starting location. We'll go x1 all the way down to xn, which is our final location. Some general location will be a plus I bunches of delta x. So we are going to take that continuous mass distribution. Once again, there's some coordinate axis attached to it. Starts at A, which is x naught, and it ends at B, which is xn. We're just going to subdivide it into little portions of length delta x, so on and so forth. In the first subinterval, there's going to be some sample point x1 star. There's going to be some sample point x2 star in the second one. The approximate mass in the first segment is simply going to be the mass density at that first sample point times the length, because this has units of mass per length and this has units of length. So those will cancel out. The approximate mass on the second subinterval would then be rho at the second sample point, delta x. And if we approximate the total mass, what we're going to get is a sum from I equals 1 to n, where we sum up all of these mass densities times this delta x. Now, if this density function is continuous on that interval a to b, that means this Riemann sum will exist when I put it into a limit. So that means we are going to define the total mass of this continuous distribution as the limit as n goes to infinity, sum I equals 1 to n, rho of xi star, delta x. And because we are assuming that my function is continuous, I know that this will translate into an integral of this density function. That's how I'm going to come up with the total mass. Now, at the same time, I can also define the total moment. The total moment is simply going to be the limit as n goes to infinity of the sum of all of those individual moments. I know by my argument above that the mass at this subdivision I is simply going to be rho of xi star delta x, and then I will have this xi living in the front here. Now, I can choose that sample point xi to be wherever I would like, so I'm also going to call this xi to be at the sample point. And if, once again, rho is continuous on AB, that means this limit exists, and the total moment will also be an integral of x rho x dx. And that means that I'm going to define the center of mass for this continuous distribution as the integral of x rho x dx divided by the integral of rho dx, which is just the total moment over the total mass. The total mass can't be zero. We will have a center of mass of a continuous distribution. And the center of mass you can think of as saying, I'm going to take this bar and put a fulcrum or a pivot underneath somewhere, and it's going to be balanced when I keep it at that point. We can extend this to a two-dimensional continuous mass distribution. We've got a thin plate, and we would like to put a pivot point there. There's going to be some location or some coordinates of the center of mass, x bar and y bar. These are now going to be the center of mass, and I would like to somehow find these points. So this type of object is sometimes called a lamina, which is a two-dimensional shape that is very thin, essentially ignore the thickness. We are going to assume that it has an area density given by this function rho of xy, and it's going to be continuous. What we're going to do is place our lamina something like this, and as always, we're going to put it inside of a bounding rectangular box. So we are going to start with this rectangular region, AB crossed with CD. And then once we have the tools in place for that rectangular region, we'll be able to extend it to a general region like this. What is the mass of this region given that it has a variable density? So what we're going to do is subdivide this region R into X and Y partitions. They're going to be N equally spaced in each direction. X partitioning into x0, x1, all the way up to xn. Delta x is b minus a over n, and then xi is just a plus I delta x. Our y will be partitioned into something similar, all the way down to yn. Delta y will be d minus c over n, and we'll have a general point c plus j delta y. So effectively what happens is we are going to subdivide this entire region here into small little rectangles. And there will be some general rectangle Rij. What is the mass in this Rij? And we're going to make an approximation as always. We are going to assume that this rectangle Rij has some sample point xi star, yj star, and then the mass in rectangle ij will be approximately the density at that sample point times the area of whatever that mass unit is. The total mass, which is an approximation again, will be approximately a double sum I equals 1 to n, j equals 1 to n of all of these rho xi, yj star, delta a's. And because this is a Riemann sum, what we're going to see is that this will turn into an integral. And because rho is continuous over this rectangle R, that's going to be our assumption here, we will define the mass of this 2D distribution as the limit as n goes to infinity of that double sum or that Riemann sum. This is now going to turn into an integral. And so this turns out to be the integral of the density function over that region R. Now what you can then do is extend this to a general region D that's been bounded by some rectangle R. Remember, we extend it as follows. We're going to take our function to be equal to rho of x and y if we are in D, and it's going to be 0 if we are R but not in D. What that does is it allows me to say then that the total mass is simply the integral of this density function over that general region. As before, I can use the Fubini theorem to evaluate this. Once we've got the mass in place, what we are going to do is define the center of mass coordinates using integrals as we had done before. We're going to treat x bar and y bar independently. So it's just a combination of two 1D calculations. So x bar is then going to be the limit as n goes to infinity of this double sum I equals 1 to n, j equals 1 to n, xi star times the mass ij, xi star, rho of xi star, yj star, delta A. And once again, this is a Riemann sum, and this is going to boil down to x times rho xy integrated as a double integral. And that, once again, we can use Fubini's theorem. And similarly, y bar can be calculated as a double integral of the y coordinate, rho xy dA. When we've got this two-dimensional lamina, it's essentially telling us that if we are placing it on some coordinate grid, these are the coordinates of the center of mass. If I were to hang this by a rope at that point, it would balance. Or another way of thinking of it, if I were to put this on some sort of stand right at this point, x bar, y bar, it would balance. Now note, if this density is constant, what we're going to find is that the center of mass calculation simply boils down to something like this, where the densities can be pulled out of the integrals, and we'll just get that following result. So it's independent of the density. Same thing happens here in the y direction. We could pull out the density and we would get the following. The densities would cancel out, and once again, it's independent. When you have a constant density, it depends simply on the geometry of the region and not on the density. In this special case, this center of mass coordinate is called the centroid. Now, another strange notation, if we talk about the x center of mass, what we're doing is taking our 2D mass distribution. And what we're talking about is trying to find the moments of each one of these infinitely many different masses in the x direction. So because we are talking about left-right, we are defining all of this relative to the origin, which in this case is x equals 0, or the y-axis. So sometimes this x bar calculation is called my over m. So it's the moment about the y-axis. Now, similarly, when we're trying to calculate y bar, what we're doing is taking our coordinate axes and we're trying to figure out the masses here relative to y equals 0, or the x-axis. So sometimes this calculation here is called mx over m. And this top part is called the moment about the x-axis. However, those names are confusing, and I would recommend that you don't bother using them. So let's take a look at an example here. So let's find the center of mass for this region that's given as follows. We've got a triangular region that intersects the x-axis at 4, and this coordinate here lives at the point 1, 1. We are going to need to calculate these integrals, and in order to do so, what we need to know is the density. So we are going to assume that the density here is just the function x, which is nice and continuous. So to begin with, let's talk about the mass, which is essentially saying calculate the integral of x dA. Now what we're going to do is say that D is a type 2 region. We're just going to talk about horizontal slices. The y coordinate is going to go from 0 to 1. This line is y equals x. The line L has a slope of 0 minus 1 over 4 minus 1, which is negative 1/3. So this line is y minus 1 is negative 1/3 into x minus 1. Or if you were to simplify that, y is negative 1/3 x plus 4/3. Which you could then rearrange as x is 4 minus 3y. So the equation here tells us that the x limit goes from y to 4 minus 3y. So if we wanted to calculate the mass, it's going to be a double integral 0 to 1 y to 4 minus 3y of x dx dy. So this integral is straightforward here to begin with. We're going to get an x squared over 2 evaluated from y to 4 minus 3y. And then that result will have to be integrated in y. What you're going to end up getting is a half 4 minus 3y squared subtract y squared dy. If you expand everything out, this term simplifies to 16 minus 24y plus 8y squared dy. If you were to calculate this antiderivative, you'd get 16y minus 12y squared plus 8/3 y cubed, evaluated from 0 to 1. Plugging everything in and simplifying it, you will end up getting 10/3. So the mass of this region is 10/3 units. We need to find the moment about the y-axis, so calculate x times a row of x and y dA, which is an integral 0 to 1 y to 4 minus 3y x times another x dx dy. This is going to be an integral of an x squared, giving me an x cubed over 3, evaluated from y to 4 minus 3y, and the result will then need to be integrated. You'll get a 1/3. This is going to be a 4 minus 3y cubed subtract y cubed dy. Do not expand that cube. You're just going to run into mistakes because of arithmetic and algebra errors. So instead, what you should do is be performing a substitution. And when you perform a substitution, you'll say that u is 4 minus 3y here, du is 3 dy. This integral will be straightforward. This is going to give you a 1/4. And at the end of the day, I'll save you the work. This is going to end up giving you an 85 over 4. So what you'll end up getting is a 1/3 times a 1/4, 85 minus 1, because each of these has a factor of a third and a fourth, giving you 84 over 12, which is just 7. The x position of the center of mass is going to be 7 over 10 thirds, which is 21 over 10. Now, to calculate the y center of mass, we're going to need the integral of y times this density, which in our case is going to be an integral 0 to 1, y to 4 minus 3y, y times x dx dy. The y can be removed from that inner integral. This inner integral was the same integral that we calculated when we did the mass calculation. So this will end up giving me a y 16 minus 24y plus 8y squared all over 2 dy. So this is going to end up giving me 8y minus a 12y squared plus a 4y cubed dy. This will give me a 4y squared minus a 4y cubed plus a y to the 4 evaluated from 0 to 1, which is just going to be 4 minus 4 plus 1, which is just 1. The y center of mass ends up being 3 over 10. So the coordinates of the center of mass are 21 tenths and 3 tenths. And if you take a look at the original region that we had here, this lived at 1, 2, and 3. The center of mass position would be somewhere around here at 3 tenths and 21 over 10.